The best way to, if you reach a spot in I3, if you just take I3 out, it leaves you with a very nice equation. Which cancels down to an A.
They do that with the hydrostatic thing, don't they? So 2 by 3 equals 1 from the get-go.
No, you just pull it out. So you just pull it out, and then you've got it on the bottom as well. It cancels with the top. But yeah.
Oh, this is what I've been doing.
Okay, let's start. So, today first I'm going to comment a little bit on your feedback. So first, thanks very much for the feedback. It was quite constructive and helpful, I think. So, I've written down a couple of points that many people mentioned, and I'll say what I can do about those. So one point mentioned on your feedback was that several people wanted more hints on the problem sheet, and I've already sent you an email about that. So from now on I'll make 2 versions of each problem sheet. One version will have plenty of hints, the other version won't have any hints. So yeah, you can just look at the version without hints first if you like and try, and if you don't get anywhere you can look at the second version, and maybe the hints will help you. I think that's a good compromise. So I'm not making the exercises too easy for those who want a challenge, but those who want hints can have a look. Okay, so this was one point. The second point was that some people wanted to have printed versions of the problem sheets every week when they come out. Yes, I can do that, why not? So from next Wednesday on, I'll bring a couple of printed problem sheets and I'll just hand them out to you. Then I think by far the most frequent comment was that I should discuss more problems during class. And I agree that this would be great, but I really can't, because there's just no time. So if we had 4 hours per week, yes, sure, I would do twice as many exercises, and that would be great. But there's still so much content to get through that I can't spend much more time on exercises during class. So my reply to this is that first, before the exam, there will be the revision week in which we have time to talk only about the problems, and you can ask me anything. Second, if you want to see me present exercises, you can always come to my office and ask me. I can run you through an entire exercise if you want. So please do that. In addition, you can ask me via email. In addition to that, the solutions to each problem sheets go online 1 week after they come out. So if something hasn't been discussed in class, have a look at the solutions. Maybe things will become clear then. Okay, so this was discussion of problems in class. The next point was that I should give more examples during the lecture. When I give a definition, then I should make examples to make the definition clearer and to just slow down the pace a little bit. Yes, I'll do that. I've already done this for some definitions, but yeah, I can try and give more examples than I have. Then one comment was that I should ask for questions more often during the lecture. So, and to be honest, I thought that I'm already doing that. I can understand that it can often be hard to follow the long proofs. And maybe if I do the entire proof and then ask for questions at the end, maybe that's not enough. Or maybe I can also imagine that when I ask you for questions after a long proof, maybe you sit there and look at the proof and you don't have the feeling that you understand everything, but you don't have specific question to ask in your head. And maybe this can lead to students not asking questions, even though they feel like they haven't understood the proof completely. And I just want to say, you can just ask me to explain the entire proof again, or to just repeat everything, if you don't have any specific questions in mind. So you can always do that. And in addition, you can always stop me, even if I don't ask you to ask questions. You can always stop me and ask, this thing isn't clear to me, and so on. So basically my answer is I can try and repeat the entire proof more often than I have in the past. And then there was a comment that said some people would like to hand the problem sheets in on Friday rather than Wednesday. If you want, that's fine. Yes, don't take too long. But if you want to hand them in on Friday rather than Wednesday, yes, that's fine. No problem. Okay, so this was that's what I thought about the feedback. So I think it helped me. I'll try to explain stuff better and ask for questions more often, and maybe spend a little bit more time on problem sheets during class, but there's not much room. So that's my reply. If you have any additional comments to make right now, you're very welcome. If you're happy with what I just said, we can also just start the lecture. So does anyone have any reply to what I just said? Okay, so if not, then let's start the lecture. You can also write me emails if you think of things later and so on. So, so it's Friday, so we start with a discussion of some problems. There's one thing that I want to discuss first, because I think the definition of simple functions, I think there might have been some misunderstanding of the definition of simple functions. So I'll start with that. So let me write down the definition again. Okay, so assume we have a measurable space, x sigma and so on. I'm not going to write that. And then a function from x to r. And such a function is quite simple by definition if it has the following representation. If it can be written in the following way. Phi equals some ci characteristic function of ai, where ci are non-negative numbers and ai are measurable sets. And the sum is finite. So there are finitely many terms in the sum, and it's just a linear combination of functions which are constant on measurable sets. So this is the abstract definition, and then on problem sheet number 5, there were some examples where you were asked to decide whether a given function is a simple function or not. And the first, so this was part A, exercise 2. The first one was so the measurable space was the real numbers together with the Borel sigma algebra. And then the function was the characteristic function of the real numbers minus the rational numbers. And the task was to decide whether this was a simple function or not. So let me give this question back to you. Is this function simple? Yes or no? And why?
Yes.
Yes, because?
Just if the correct form is like a sum from I equals 1 to 1, and R without Q is Borel, because Q is countable, so Q is Borel, so the complement is Borel as well.
Exactly. That's exactly right. I don't have anything to add to that. So this function chi the complement of the rational numbers can be written as 1 times itself. And this is precisely this with only one term and coefficient equal to 1. And as you rightly said, this set below here is measurable because Q is countable, and we've shown that countable sets are Borel measurable, and then the complement of Q is also Borel measurable. So this function is a simple function. Quick sanity check. What about this function chi Q? This should be simple as well, right? Because it's of the same form, just a characteristic function of a different set, but Q itself is also measurable. So, and all we need is to have this form with measurable sets down here. So yes, that's simple as well. Yeah, and I think I'm just going to continue with this exercise now. So, the next part B of this exercise was okay, so part B was a Borel measurable function. So the sigma algebra is again, the measurable space is again this one. Then we have a Borel measurable function from R to R such that its image is a finite set. Is it simple or is it not simple?
Yes.
Why?
If f of R is finite, you can just write it as a set of like n elements, and then you can decompose f as like those elements times the characteristic function of the pre-image of that element, and sum them up.
So maybe it's best if you dictate and I write.
Okay.
So you say yes, and then
so f of R f of the real numbers equals like a set.
Equals?
A set. So
equals.
do the set
We want some kind of
like. Yeah.
Okay. Let me call them y.
Yeah. And then now you can write f equals somewhere else. So it's y1 times times the chi of the pre-image of y1. And like the same thing but with all the indexes.
Like this?
Yeah.
Okay, so let's see what we got. So this was good, but it's only almost true. So let's see what we have. We have, I mean, this is clearly right? We've assumed that it's the image is a finite set, so we can write it as a finite number of points. Then we have this representation, yes. This representation is of this form. Fine. Now there are two things left to check. The first thing is these sets down here have to be measurable. Are they?
I think so, because I think there's like a lemma which says pre-images of sets are all measurable.
Yes, so if f is Borel measurable, then pre-images of Borel sets are Borel measurable. So yes, these are measurable. That's fine. But then we have this. There's nothing in the assumptions that says f is non-negative, right? So it goes from R to R. These y's could be negative. And that's the only reason why this is not a simple function. So this exercise was a little mean because yeah, you check all the difficult stuff and then it's this thing that fails. So this is not simple. Because these yi could be negative. But indeed, if the function didn't go to R, but to the non-negative real numbers, then it would be simple. Then this argument would exactly prove that f is simple, because then these yi would have to be positive, and then all the things here would be satisfied in the definition of the simple function. So the takeaway from this is that, okay, first, simple functions have to be non-negative, but second, yes, simple functions can be interpreted as non-negative functions, non-negative measurable functions, which only assume a finite number of values, such that the image is a finite set. That's another characterization of simple functions, if we know a priori that it's non-negative and measurable. Okay, are there any questions so far about part A or part B?
Part B, do you need a counterexample, or is it enough to say that it's not simple from that?
Well, it's not. I mean, the statement here is it's not necessarily simple. Of course, for specific f, it could happen that it's non-negative. But as soon as f becomes negative somewhere, then one of these yi must be negative. And then that's a counterexample. because if it's negative somewhere, then you can't find such a representation. It's impossible. Because if there was such a representation, it would be positive and non-negative everywhere. Because, I mean, this is always 1 or 0, and this is always non-negative. Was that clear?
Yeah.
Okay. Any other questions? Okay, so this was part B. C was the following function. F of x is plus infinity if x is in Q and 0 else. On the same measurable space. Is this a simple function, yes or no?
No.
Why?
Because the simple function can't give infinity.
Yes. Can you explain why? Can you
It's a finite sum of finite of it's a finite sum of real numbers.
Yes, that's right. So yeah, so basically this is where infinity is forbidden, right? The target space is the real numbers, and not the extended real line that has plus and minus infinity. So yeah, by definition, it has to be finite everywhere. And then of course these numbers Ci, they also have, they can't be infinity. They have to be finite real numbers. And that's the reason why this is not simple. Okay, and then there were two more examples of functions. The first one was the first one was this. So it's an infinite sum of characteristic functions with a prefactor that makes it converge, basically. So this 2 to the minus n makes f of x finite everywhere. No, that's not true. It's finite. It's finite anyway because these intervals here, n from n to n plus 1, they're disjoint, right? So yeah, it just has some values 2 to the minus n on disjoint intervals. Is this function simple or is it not simple?
sum is infinite.
Yes.
It's not simple.
Okay, so that's true. It's true that it's not simple, and it's true that the sum is not finite. Now, that's not quite a proof yet, because well, this is a bit sloppy, but being simple means there exists some representation with a finite sum here. So there might exist a different representation of f of x, which has just a finite sum. So if you want to prove that it's not simple, you have to show that there exists no such representation like this.
Because f takes a different value on all of the infinite terms, infinite many terms.
So
because the characteristic functions, when their union makes up the whole positive real numbers.
no, it's not because of that. Because imagine this 2 to the minus n was gone. Then would it be simple or would it not be simple? It would be simple, because then it would just be a constant function 1 everywhere. So it's just 1 times characteristic function of R. So in that case it would be simple, because there exists a different representation with the finite sum. Yeah, so it's got nothing to do with the support covering the whole line. Yes?
It can't be simple because its image isn't a finite set.
That's right. That's exactly right. Yeah, can you like dictate the proof for me?
You get a different image for like each interval. You move one along and then you get a different image because the 2's then.
Huh?
Like there's a different power of 2 is assigned to every interval.
Yeah. So yes, I'm going to try to put this into a longer proof. So, but that's the key point. So the image of this function. So let me just write not simple. Because the image of this function is 2 to the minus n, and n. Right? All the values of 2 to the minus n are in the image of it. And then, oh, actually, 0 as well. This is an n. Sorry. This sum goes from n equals 1 to infinity. So for every negative x, this gives 0, because these characteristic functions are only on the positive half line. So the image is this. Okay, so the image is an infinite set. But then yes, in B, we've seen that one characterization of simple functions is non-negative measurable with finite image. So basically in B, we've shown that if the image is finite and the function is non-negative and measurable, then it's simple. But the other direction is easy, because if there exists such a representation for a function with finitely many ci, then the image has to be finite. The image is just well, it's not a subset of the ci, but it's a subset of sums of the CI. And if there are only finitely many CI, it has to be the image has to be a finite set. So I'll explain this again. So the image of a simple function has to be a finite set because there are only finitely many CI. So take some fixed x, then phi of x is this sum. Then these are finitely many AI, so x will be contained in at most finitely many of these AI. Then phi of x will be a sum of finitely many of these CI. And this will be true at every point x. But the set of sums of the CI must be finite because there are only finitely many CI. So that's why simple functions, the image of simple functions is always a finite set. And here that's not true. Was that clear? Any questions? If that's not the case, then let's look at the last example briefly. Okay, so in the last example, the function is, the definition of f is similar, but the sum goes not to infinity, but just to 50. So is this function simple or not?
Yes.
Yes. Because?
It's non-negative and the image is finite.
Yes, that's one reason, yes. Also, I mean, you can also use the definition directly because this is such a representation. So it's already in the right form. You just have to check that everything works out. So these intervals have to be measurable sets, and these prefactors have to be non-negative, but that's the case. And the sum has to be finite, which it is. So this is simple because it's already in the right form. Okay, so this was the exercise about simple functions. Yeah, I think it was good to do that. Yeah, maybe we could do, so on sheet 5, all the exercises of part B were rather short, so maybe we can do one of them now, and then move on with the lecture. I guess not everybody has sheet 5 in front of them, so I'll just ask you which exercise you want to see of the remaining 4, and then we'll do that. So the first exercise was in the first exercise, there was a simple function on the real numbers was given, and the exercise was to rewrite this with different intervals and to get a new representation. The second exercise was the second exercise was we have a measurable space with sigma-algebra, the minimal sigma-algebra. So we have a set X and then some subset A of X, and then we just take the sigma-algebra that consists only of empty set A, X minus A, and X. And then the task was to find all measurable functions on that measurable space. The third exercise was the third exercise was given a measurable space and a subset A to find the characterization for the measurability of the characteristic function of a set. And then the last exercise was given a measurable function, non-negative, then if the measure of the set where f is positive, if that set has positive measure, then there exists positive epsilon such that the set such that the set where f is larger than epsilon has positive measure. So these were the 4 exercises on sheet 5, and now I'll just ask you which one would you want to see, which solution. Any opinions? we'll have to do a poll. Who wants to see number 1? Who wants to see number 2? Okay. Who wants to see number 3? Who wants to see the last one? That's the majority. Okay. So we'll do the last exercise. Okay, so for this last exercise, there was a hint. Yes, and the hint was to consider the set. I'll just do it. Yeah, so the central idea was to realize that the set where f of x is positive, so the one on the right hand, the one on the left hand side, can be written as the union n equals 1 to infinity of the set of all x such that f of x is larger than 1 over n. Now it's pretty clear that this is true because this inclusion is clearly true, because if x is in the right hand side and then the set on the right hand side, then f of x is larger than 1 over n for some n, so it has to be positive. So this inclusion is clear. The other inclusion, that's also fairly clear, because if x is in the set on the left hand side, then f of x is positive. But then if f of x is positive, then there exists an n such that 1 over n is less than f of x, right? And then x must be in one of the sets on the right hand side. So we have this equality. And then not only do we have this equality, but these sets without the union, they're increasing. So x in x such that f of x is larger than 1 over n is subset of x in x such that f of x is larger than 1 over n plus 1, because this condition is weaker than this condition. So we have this inclusion. And this holds for every n. So this sequence of sets is increasing. And now we have an increasing sequence of sets, and we know something about the union of these. And now, in the hint on the exercise sheet, the hint already said to use the monotone convergence theorem for sets. And it's clear that we should do this because we have an increasing sequence of sets and we know something about the union. That's precisely the situation where the monotone convergence theorem for sets gives us information. So monotone convergence for sets, that's theorem 216. Implies that what does it say? The monotone convergence theorem for sets says that this union can be written as a limit. If you apply the measure mu to this, then mu of the union can be written as a limit of mu's. So more concretely, mu of x in x such that f of x is positive. So that's this left-hand side, which is equal to the right-hand side. So, and now the right-hand side, if we apply mu, we can write this as a limit. Limit n goes to infinity, mu of this x in x such that f of x is larger than 1 over n. Okay, now let's go back to what we wanted to prove. We wanted to prove that if this left-hand side is larger than 0, then there exists an epsilon such that the set where f of x is larger than epsilon has positive measure. So from the assumptions in the exercise, we know that this left-hand side is strictly positive. So the right-hand side is also strictly positive. Yeah, I'm just going to write this. Okay, but now the right-hand side is the limit of something. And we know that when the limit of a sequence is strictly positive, and the limit of something is strictly positive, then that sequence has to be strictly positive even before it reaches the limit, right? So definition of limits essentially implies that there exists a number n0 such that this thing mu of x in x such that f of x is larger than 1 over n0 is positive. And now this is the same as the statement we had to prove, because we had to show that there exists some epsilon. We can choose epsilon equal to 1 over n0. And then this statement is precisely the same as this last statement. And this was exercise number 4. Yeah, are there any questions about exercise number 4? Are you all happy? Okay, so yeah, the trick was to use the monotone convergence theorem and to realize, yeah, that these sets are increasing. And then the last step was to untangle this limit and realize that, yeah, if the limit is positive, then even before you take the limit, it has to be positive for some n. Okay, so if that's clear, then I suggest we continue with the lecture. Oh, actually, yeah, we should take the break now, shouldn't we? Yeah, so let's take a 10-minute break and then continue at 2:10.
Yeah, that's good. Yeah, I thought it was Is anyone interested in relativism? Probably interested. Yeah. Like application based.
All the
people were interested.
one of the applications.
It was different poster, like
white stuff like board.
research pretty much followed the like but like methods, results, etc.
You always say in the hallway that you can't be on chalk.
And I think a lot of people just felt like commenting. And then that would be like, so that would be a way for me to
Not a lot.
That's the theorem. This is just h is a proportion of such things. That can be rewritten
And for the weekend now as well. To a bit about there actually. Yeah, start with
she like came up
and then check it over this. And then h is a proportion, so I need to So this equation basically models this how calcium would be raised into itself. So this is the and then she's sort of like do not know how to use it. Because normally what happens in a simple process is you don't have to change, you just get a single scan and you have to convert this out of 1 divided by the total to get them out of 1. And you can just take that over here. I've got, I don't know if I just like that one, depends on which is which. And also things in the quotients.
I mean, it's not online, but
it's going to be
that was a fun meeting. Yeah.
So
like you had the yeah, it was just like the idea was
that's on the bottom, so I can't ever expand that.
with each simulation you like trigger the alarm.
I wondered if it was getting the story was going
Trigger the alarm every time. It goes by the threshold. But what I was doing is
I'm not actually meaning
you were supposed to stop after the first
basically, yes. A large portion of it is this situation stuff. If it was something like two like
no, not really. We haven't
it's really
that many. The first one's quite
I mean, from that's the proportion. That's just like the concentration. The scale.
But now it just has to
Like if I had like simple
quite formal really.
So imagine you have channels and cells that open and close. It's just a proportion of open channels.
That's disgusting.
Yeah, and C
Or you mod it as a true
Specimens.
Oh, just H itself rather than
yeah.
okay.
Because I keep forgetting like basic definitions.
It doesn't work. But it must work some way, but I'm not clever enough to spot it. And I don't want to try everything because it will take too long.
Yeah, just spending way too much time keeping up to date with content.
Yeah, I imagine that's what I before.
Plug in your stuff into
Also, yeah, half
so
a big data.
I'm trying to think of
It's like 20 quid a piece.
master
So it's like, you know, when we do the law of transaction, you get a differential equation, but it's different each time.
Yeah.
So you can get a master equation, but it's different each time.
Oh, I see.
It's like a standard thing.
Absolutely zero application.
Yeah, it's called a master equation.
Yeah.
And then on the
Okay,
master
let's continue.
here's an example from that.
So the last thing we did last time was to define the back integral for functions which are allowed to be negative. So up to this point we could only integrate functions which are measurable and non-negative. And then the last thing we did last time was to define the back integral for arbitrary measurable functions by just taking the positive part and taking the negative part, and we could easily integrate both, and then just take the difference. And then we've given all these names. So f is called integrable. By definition, that's the same as writing f is in L1 of this measurable space, which by definition means that this integral is finite. And this integral being finite is the same as both the integral of the positive part and of the negative part are finite. Yes, and to define this integral we had to assume that either the integral of the positive part is finite or the integral of the negative part is finite, because we're taking a difference here and we can't subtract infinity from infinity. So yes, so if one of them is finite, then this thing can be defined, can be written down, and then we call it integrable if the other one is also finite, so if this entire thing is finite. Okay, and this is where we stopped last time. And then there are some simple properties that we can infer immediately from this. So the first is f is integrable in this sense if and only if if and only if f is measurable. The integral of the absolute value of f is finite. This is just because the absolute value can be written as the positive part plus the negative part. So you immediately get this criterion. And the second remark is just about notation. So common notations for the integral are the one that we always write, integral over x f d mu. If you want to emphasize the dependence on the variable, you can some people write integral f of x d mu of x. And if you're really lazy, you just write integral f. If the measure is clear from the context, for example. And then in the case of the Lebesgue measure, then instead of dm, people write dx. So the notation for the Lebesgue measure, most people use the same notation as for the Riemann integral, just integral f of x dx. this is all stuff that you might see in textbooks. All of these notations mean the same thing, just this integral. Okay, are there any questions about this definition, this remark? Okay, so I think this is fairly intuitive. You just take the positive part and the negative part and you subtract the integrals. Well, and now we're going to study this integral and derive properties of this integral. So the first thing, it's called remark again, 4.35. So the first thing is, if f is integrable, then necessarily it's finite almost everywhere. Now, this isn't completely obvious, but it's also not hard to prove. The proof goes like this. It's just by contradiction. We assume that the magnitude of f is infinite on a set of positive measure, and then we show that it can't be integrable. So if f is infinite on a set A in sigma, and mu of A is strictly positive, then we can look at the integral of the absolute value, integral absolute value of f d mu. And we integrate over yeah, that's fine. So then this integral can't be finite, which means that f can't be integrable, right, by this remark. So this is bounded from below by integral characteristic function of A times absolute value of f and this is bounded from below by integral x n times characteristic function of A d mu for every n in n, because magnitude f is infinite on A. So for every n, it's larger than this function, n times characteristic function of A. But now this integral can be computed, right? Integral x mod f d mu is then larger than n times mu of A for every n in n. But then, because mu of A is not 0, this has to be infinite. So it can't be integrable. So if f is integrable, then it has to be finite almost everywhere. Yeah, so really integrability is connected to boundedness of functions and to, yeah, it can't be too large. Okay, this was the first remark. And the second is just that the opposite is not true, but that's pretty clear. So if mod f is finite almost everywhere, then it's not true that f is integrable. And the second point is pretty clear. I mean, take, for example, take the real line and take the Lebesgue measure. Then you could just take the function which is constant 1 everywhere. Then the integral of that is infinite, so it's not integrable, but the function itself is finite everywhere. So the second point clearly here. Finiteness almost everywhere does not imply integrability, because the measure of the space could be infinite, basically. Okay, any questions? The really important stuff begins. So this next inequality is pretty simple, but it's really, really useful. So start with a measure space. And a function f in L1 of x sigma mu. So an integrable function, then the magnitude of the integral of f is bounded above by the integral of the magnitude of f. This is really, really useful. You need it all the time if you study differential equations, for example. So this is really basic, but really, really useful. And the proof is really simple. It's just yeah, it just follows from this definition basically. So write down the left-hand side, integral f d mu, absolute value, and now this is the same by definition as integral f plus d mu minus integral f minus d mu, and now we have the absolute value and two terms. We can use the triangle inequality of the real numbers, and then this is bounded by integral f plus d mu plus integral f minus d mu. But now I can delete the absolute values, right? Because f plus and f minus are non-negative functions, so these two integrals are non-negative anyway. And now, because all the integrands are positive functions, we can use the linearity for non-negative functions that we proved earlier. And then this is the same as integral f plus f minus d mu, which is the same as integral absolute value of f d mu. So this equality uses the positive linearity of integrals that we shown either last time or the time before that. Because f plus and f minus are non-negative functions. Any questions? Okay, so as I said, you remember we proved linearity for non-negative functions, linearity of integrals, for non-negative functions and for non-negative numbers multiplying with these functions. And what we're going to do now is extend this to real linearity of this integral that we defined now. So the next proposition is let x equal mu be a measure space fg integrable functions and let alpha, beta be arbitrary real numbers. So they don't have to be positive or anything. Then alpha f plus beta g is integrable and the integral alpha f plus beta g d mu is the same as alpha integral f d mu plus beta integral g d mu. So this is what we're used to from Riemann integrals, and yeah, this should really be true. Otherwise, that would be strange. And the proof has several steps, and it's surprisingly tricky in the end. So what we're going to do is first we're going to show that you can pull this real number out of the integral, and we don't change the integral. And after that, we'll show this additivity, so that the integral of f plus g is integral f plus integral g, and then together this will imply linearity. So step one is to show that multiplication by real numbers can be swapped with integration. So step one. Take an an integrable function f. And first we restrict to even to non-negative alpha. So f is this some integral function. It could be negative somewhere. Alpha is non-negative. Then integral of alpha f is the same as, we just use the definition of the integral. Alpha f positive part d mu minus integral alpha f negative part d mu. But then multiplication by alpha and taking the positive part can be swapped because alpha is non-negative. And the same for the negative part of f. So this is the same as integral x alpha times positive part of x minus integral x alpha times negative part of f d mu. And now each of these terms is an integral of the type that we've studied before. So this integral is just an integral of a non-negative function, and the other one as well. And for integration of non-negative functions, we know that it's linear if alpha is non-negative. So we can again use this positive linearity from last time to just put alpha in front of the integral. D mu minus alpha integral f minus d mu. And now this is alpha integral f d mu by definition. So really everything we do now is just split functions into positive and negative part and then use what we know about those, because those are non-negative measurable functions. So this is step one. So non-negative real numbers we can pull out, that's fine. Step two. Step 2 we'll do it for alpha equal to -1. And then if we know that it's true for non-negative alpha and we know that it's true for alpha equal to -1, then it's true for every alpha, for every real number. Because you can write every real number as a sign times a non-negative real number. So to show it for alpha equal to -1, we do the same thing. We use the definition. Integral minus f d mu is the same as integral of the positive part of minus f minus integral of the negative part of minus f. And now if you go back to the definition of positive and negative parts, it's easy to see that the positive part of minus f is in fact the negative part of f. Yes. And the negative part of minus f is in fact the positive part of f. And now this here is just the definition of integral f with a minus sign. So yeah, for alpha equal to -1 is even easier. And here we use that minus f positive part is negative part, and so on. So this was step 2. And now step 1 plus step 2. Imply that integral alpha f is equal to alpha integral f for every real number alpha. Okay, and now what's left is to show additivity of the integral. And that's surprisingly tricky, because you have to pay attention to a lot of details. Okay, to show additivity, well, we take two functions, f and g. And we assume that they're integrable. And then we have to look at f plus g. So let's give this a name. H equals f plus g. So the first thing we have to check is that this is even well defined, because f and g can be infinite. But it's gone now. But we had this remark that said if a function is integrable, then it's finite almost everywhere. So we know that f and g are finite almost everywhere. So h is, so we can definitely define h on the set where both f and g are finite. But that's fine, that's almost everywhere, because the set where f or g are infinite, that's the union of two null sets, which is still a null set. Yeah, so the thing that could go wrong here would be that f is plus infinity and g is minus infinity or something like that. And then this wouldn't be defined. But this can only happen on a set of measure 0. Because f and g are finite almost everywhere, because they're integrable. Yeah, so what we can do, so now h is defined almost everywhere, and what we can do is just put h to 0 on this null set where it's not defined, because it doesn't matter, it doesn't contribute to the integral. Okay, so now h is well defined, and now h has to be integrable because we want to integrate it. So the next thing is the following. So if we look at the positive part of h, then that's bounded by the positive part of f plus the positive part of b. that's really easy to see if you go back to the definition of the positive part. It's really, you look at it and it takes 2 minutes to realize this. And for H minus, it's the same thing. This is H minus is bounded by F minus plus G minus. That's easy to see from definition of F plus F minus. So I mean the definition of positive parts and negative parts. But now from these two inequalities we can conclude that H is integrable, because F plus and G plus both have finite integrals. H is bounded by F plus and G plus, so H plus has finite integral. And the same for H minus. So from these two inequalities it follows that H is integrable. The integral of H is finite. Yeah, this follows from the monotonicity of integrals, if you like. So again, this was part of the section where we only studied non-negative functions. Because H plus F plus G plus are non-negative functions, so we can apply the entire section to this function to deduce things. And one of the things there was monotonicity of integrals, which said that if H plus is less than F plus plus G plus, then the integral of H plus is also less than the integral and so on. So the integral must be finite, so H is integrable. And now finally we're allowed to write down the integral of H. So first what we're going to do is write H like this, H plus minus as minus. And by definition of H, this is the same as F plus G, so F plus minus F minus plus G plus minus G minus. And again, we want to apply results from the previous section about non-negative functions. So we have to sort all these terms such that we're left with non-negative functions, because we can say something about them. We can do this, H plus plus F minus plus G minus equals F plus plus G plus plus H minus. Now on the left hand side there's a non-negative function, and on the right hand side there's a non-negative function. And now we can integrate these, we can just integrate both sides. Integral H plus and then we can use additivity of integrals for non-negative functions from the last section. So that's why integrating this, we can write this as integral. Yes, on the left-hand side we integrate this. We have an integral of this entire sum, and then we can decompose it as 3 integrals. And then we do the same thing for the right-hand side, and we get integral F plus d mu plus integral G plus d mu plus integral H minus d mu. And now this is it. We can just sort all the terms again. So we can subtract this thing again and put it to the left-hand side, and so on. That gives us integral h plus d mu minus integral h minus d mu. And then we do the same to f and g. So everything that contains f and g comes to the right-hand side. That's integral f plus d mu minus integral f minus d mu plus integral g plus d mu minus integral g minus d mu. And now we just look at this, and on the left-hand side we have the definition of integral h. On the right-hand side we have the definition of integral f and the definition of integral g. So this is really just the same as integral h d mu is equal to integral f d mu plus integral g d mu. And this is additivity, right? So the only thing left to say is that if you combine steps 1, 2, and 3, then this implies linearity. Okay, so yeah, step 3 was surprisingly tricky, and even this last calculation looks a bit roundabout, right? We start with just the definition of h and f and g in terms of positive and negative parts. Then we sort everything around, then we integrate, and then we sort it back. But we have to do this because we need non-negative functions on both sides in order to use the positive linearity of integrals. Yeah, and that's the basic strategy in this section. We always decompose into positive and negative parts, and then we use what we already know, because they are non-negative functions. Okay, are there any questions about this proof? Or do you want me to repeat anything? Okay, so the next proposition is again one of those that look obvious, but that we have to prove because we're in this new situation where functions are allowed to be negative. So proposition 438. Let X sigma mu be a measure space. Then the following two things hold. First, if H is integrable 1 of X sigma mu, and h is non-negative almost everywhere, then integral h d mu is non-negative. Second, if f and g are integrable functions on x sigma mu, and f is less than g almost everywhere, then integral f d mu is less than integral g d.
Is h supposed to be non-negative in I?
Sorry, yes. Thanks. Okay, and point 1. So this first point, if h is non-negative almost everywhere, then the integral is non-negative. That really looks like we've already proven it, because we had a similar theorem in the section about non-negative functions. The only difference here is that h is non-negative only almost everywhere. It's not assumed to be non-negative everywhere. So this first point is just to show if it's only non-negative almost everywhere, then the integral is still non-negative. And yeah, I mean, and then the proof is not too difficult. So if h is non-negative almost everywhere, then there exists a measurable set E such that h is non-negative on the complement of E, and E has measure 0. That's what non-negative almost everywhere means. And now integral x h d mu. We've seen this last time. We can write this as integral x minus e h d mu plus integral e h d mu and this now let me change this slightly. We use the definition of the integral. So the integral of h is defined as integral h plus d mu minus integral h minus d mu and then both these integrals I can decompose into integrals over e and integrals over x minus e. So this is the same as integral x minus e h plus d mu plus integral e h plus d mu minus integral x minus e h minus d mu minus integral e h minus d mu. But then I think we had this last time. these two integrals over E are both 0, because E has measure 0. And then on x minus E, h is non-negative. So the negative part of h is 0 on x minus E. So this integral is 0 as well. Right, because on the set x minus E, h minus is just 0, because h is non-negative there. So this implies that integral h d mu is the same as integral x minus E h plus d mu, and that's non-negative. Because this is just an integral over a non-negative measurable function. So it's an integral like the ones in the previous section, and those were always non-negative because they were defined as the supremum of non-negative things. Yeah, so we can always change a non-negative function on a set of measure 0, and the integral will still be non-negative. That's the takeaway message from point 1. Any questions? Okay, and point 2 now follows from point 1. Because we can just take, so f is less than g, so we can define h to be g minus f, right? Then that's non-negative almost everywhere because of the assumption. But then point 1 implies that the integral of h is non-negative, but that's the same as the integral of g minus f. And now, because we've proved linearity, this is the same as integral g minus integral f. So this step follows from linearity and the fact that f and g are integrable. Because if they weren't integrable, we would have infinity minus infinity again, and this would be nonsense. So linearity and integrability are crucial in this step. And now, we're done, because 0 less than this difference means precisely that integral of f is less than integral of b. So that finishes the proof of this proposition. And okay. There's 1 minute left. That's just enough to state the next theorem, but not to prove it. And again, the next theorem is one of the most important theorems of the entire lecture. It's another convergence theorem. So we've seen the monotone convergence theorem, if you remember, which said that if we have a sequence of non-negative functions, measurable, and they converge, and it's a monotone sequence, so the sequence is increasing, then the sequence of integral convergence converges to the integral of the limit. And this next theorem gives a different set of conditions under which we can conclude that integrals converge. And it's called Lebesgue's dominated convergence theorem.